Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 29 of algebraic topology. In previous lecture we saw what are CW complexes, and then we studied what is degree map because we needed this in order to calculate cellular homology, and then we defined cellular homology. In today's lecture we are going to continue our discussion with the cellular homology, and we are going to calculate some examples. We are going to calculate the homology using the cellular homology, and then in the second section we will see what is homology with coefficients. So the idea is very simple. So far we have taken the coefficients to be from set of integers. Now homology with coefficients will generalize this idea to any abelian group, and it's not very difficult, and it runs very parallel to the discussion where we take our coefficients to be from set of integers. And in the last section of today's lecture we will start a new topic called the covering spaces. Let's begin with today's lecture. So let's recall ourselves what is cellular homology. In cellular homology we have a space with given CW decomposition, okay, and remember that a space can have more than one CW decompositions, and we saw examples of circle and sphere and other examples. And in the next step we define cellular chain complexes W star X, whose group of n chains is free abelian group generated by n cells in E. Okay, so this CW decomposition E has cells of different dimensions, and for example if we want to consider WNX, then this is a free abelian group generated by n cells, so cells of dimension n from this set capital E. And then we can define cellular homology from this complex. But remember that we used relative singular homology in order to define this chain complex, okay. So how we did that? So very simply we take WKX to be equal to this relative singular homology. So what is this XK? So basically this is k dimensional space, and remember that instead of just taking this CW decomposition, there is an algorithmic way of constructing X using this cells from the capital E. Okay, so we already discussed this in our previous lectures. Okay, so in that procedure of constructing capital X starting from x0 and to x1 up to xn, okay, so we should use superscripts, okay, so x1 and xn. So in this procedure we have these x with superscripts, okay, so so these are those xi's, okay, so this is this relative singular homology, and then we define these DK maps using the maps which we already know. So for example we know what is this delta k, and we know what is this thing, so using these two maps we can define this DK, okay. So that's how we define these maps, and so these two facts, so WKX and these DK maps, so this will gives us a chain complex, okay. So using that chain complex we can define the cellular homology, okay. So this forms a chain complex, and so let's start calculating cellular homology for some spaces, but before that we are going to need a product of cell complexes, okay. So we have X and Y, which are two cell complexes, then X cross Y has the structure of a cell complex, okay. So or in other words, if we have two CW decompositions of X and Y, then let's see what will be the CW decomposition of X cross Y, okay. So let En alpha denote a cell from the cell structure of X, and E and beta. So this superscript n denotes the dimension, and this alpha is basically an indexing subscript. And similarly, in this case, this n is the dimension, and this beta is basically the subscript which is indexing these cells. Okay, and if we denote E and beta is cell from the cell structure of Y, and E and alpha is cell from the cell structure of X, then the cell structure of X cross Y consists of the products E and alpha cross E and beta. Okay, where E and alpha ranges over all cells of X and E and beta ranges over the cells of Y. Okay, so in other words, what we are saying is, for example, if we have a CW decomposition of X to be E1 up to E2 up to, let's say, E10, okay, for example. So notice that I am not writing down the dimensions of these cells. Okay, so it could be any dimension. So E1 could be of dimension 0 or 10 or 100 or 1 billion, could be any dimension. So I'm just saying that that's our space X. And similarly, if we have Y given as, okay, so let's call them E prime 1 up to so on E prime 10. Okay, so once again you can notice that I'm not writing down the dimension. So the point is X cross Y has a CW decomposition, which is going to be E1 E1 prime, E1 E2 prime, so up to so on E10 E1 prime. Okay, so E10 E2 prime up to so on E10 E10 prime. So in other words, just take the Cartesian product of this cell decomposition and this cell decomposition. Okay, so let's see some examples. So remember that S1 may have many CW decompositions. So one of them is where we have one cell of dimension 0, just a point, and one cell of dimension 1. Okay, so this is S1. Okay, so similarly we can have okay, another S1 having this cell decomposition E0 and E1. Okay, so the cell decomposition or CW decomposition of S1 cross S1 will be given as E0 E0, okay, E0 E1, E1 E0, and E1 E1. Okay, so now this is 0 dimensional. Okay, this is 1 dimensional. This is again 1 dimensional, and this is going to be a 2-dimensional cell. Okay, so remember also that S1 cross S1 is torus. Okay, so we have already seen this many times, but how this gives me a cell decomposition of a torus. Okay, so starting from this 0-dimensional cell, so let's say this is the 0-dimensional cell. So this is 1-dimensional. Okay, so we are attaching this thing to this 0-dimensional. So let's say this is this 0-dimensional. Okay, and this is once again a 1-dimensional cell, but this time this E1 is different from this E1. So let's call this like this. Okay, so now we want to attach a 2-dimensional cell with this construction. So in other words, if we just take 2 cell and attach to it, and we will get a torus. Okay, so that's how. So the fact that S1 cross S1 is a torus, we already knew that, but then why this taking cross product of the cell decomposition of S1 and S1 will give me a cell decomposition of torus is given by this argument. Okay, so similarly we can consider a cell decomposition of Sn, and remember that Sn may have many CW decomposition, but if we consider the simplest one, so in which case Sn is basically given as E0 En. Okay, so a zero-dimensional cell and an n-dimensional cell. Okay, so if we take Sn to be like this, and if we consider the cell decomposition of Sn cross Sn, then this is going to be E0 En and En E0 and En. So Sn cross Sn has the following CW decomposition. So where once again this is zero-dimensional, this is n-dimensional, this is once again n-dimensional, and this is 2n-dimensional. Okay, so the CW decomposition of Sn cross Sn, if we consider the following case, that n is greater than or equal to 2. So in this case there is no cell of dimension 1, because there is 0 dimension and then 2 dimension. There are two cells of 2 dimension. There is no cell from 3 dimension, and there are cells from 4th dimension. Okay, so in other words we can say that W4 x, so if we take x to be equal to Sn cross Sn for simplicity. Okay, so this goes to W3x, this goes to W2x, this goes to W1x, this goes to W0x, up to so on. Okay, so there is no cell of dimension 5. So this is 0 because there is no cell of dimension 3, there is no cell of dimension 1. Okay, so now remember, while calculating the homology from a chain complex such that the alternative terms are 0, then H4 of x, so the homology of x is just equal to, so basically it's going to be isomorphic to W4x. Now there is one cell of dimension 4. Okay, so because when n, so let's we are taking the case at n is equal to 2. Okay, so in particular, okay, so for n is equal to 2, so we have one cell of dimension 4, so this is going to be isomorphic to z. Okay, so similarly H2 of x is going to be isomorphic to, so there are two cells when n is equal to 2, then there are two cells of dimension 2, so this is going to be isomorphic to z plus z. And similarly when this we are considering H0 of x, then H0 of x is going to be equal to, in fact, isomorphic to z. So that's how we can calculate the cellular homology of Sn cross Sn. Let's go back and try to see that how we can calculate the cellular homology of S1 cross S1. Okay, so in this case we are going to get W2x, because there is no cell of dimension 3, and then W1x, so there are two cells of dimension 1, W0x to 0. Okay, so this is a path connected space, so with one path component, so in that case we know that this is isomorphic to z. Using this fact we can easily calculate the cellular homology of this torus, and you can confirm the results are the same when we calculated the homology of torus using singular homology or using simplicial homology. So you see, in this case it's very simple to calculate the homology of a torus. Okay, so just use this fact and everything else is very clear, because this Wx, okay, so it is generated by only one element, because there is only one cell of dimension 2 and there are two cells of dimension 1. So use this fact and use this fact and you will get the cellular homology of torus. Okay, so in order to compute the CW homology groups, we need a better understanding of the boundary maps. Okay, so this is given in terms of degrees of maps between spheres. Okay, so what is this? What are these maps? So dn en alpha. So this is equal to d alpha beta e n minus 1 beta. So where d alpha beta. Okay. So what is this thing? So remember that we are applying this dn on this n dimensional cell, and of course we should get a combination of n minus 1 cells. Okay, so of course this is always true when we are considering a chain complex. So when we apply a boundary formula, then we get a less one-dimensional less objects. Okay, so in this case the coefficients are d alpha beta. So what are these d alpha betas? Okay, so this is basically degree of the map. Okay, so what is this map? We will try to understand this. What is this map? So this is composition of the attaching map with the quotient map collapsing this to a point. Okay, so let us now try to understand this d alpha beta, and this d alpha beta is basically composition of this map. Okay, so remember that en alpha is basically an element of E, which is collection of cells, which gives us a cell decomposition of the space X. Okay, and we attached this cell. Okay, so this belongs to the cell decomposition. In other words, we have to attach this cell to let's say xn minus 1, so one dimensional less. Okay, so because when we are constructing X, then we have to do it in step-by-step way. So attach one cells, all the one cells. It could be one, it could be more than one cells. Okay, so attach one cells, you will get x1 up to so on, and if we want to get xn, then we have to attach n cells to xn minus 1. Okay, so sometimes we write brackets around it. Okay, so we have to attach all the n cells. Okay, so I'm not saying there is only one n cell, there could be more than one n cells. So we are attaching it to xn minus 1, and we are obtaining xn. So let's consider this particular instance, because we are applying this boundary formula on a particular n cell. Okay, so this particular n cell has to be attached to xn minus 1 in order to get xn. Okay, so once again, of course, there are other n cells as well, but we need to attach this n cell as well. Okay, so if we want to attach this n cell, then we need a map from Sn minus 1 to xn minus 1. Okay, so we need this map because this is the boundary of dn. Okay, so the boundary of dn is equal to Sn minus 1, and if we have this map, then we can attach this disk dn, or in other words, we can attach this cell en. Okay, so attaching en to xn minus 1 comes with this map. Okay, so this map Sn minus 1 to xn minus 1. Okay, so the next instance. Okay, so let's consider the next instance. This is the composition of this attaching map with the quotient map. Okay, so what is this quotient map? So this quotient map is collapsing xn minus 1 minus en minus 1 to a point. Okay, so if we collapse something to a point topologically, then in other words, we are taking quotient with this thing. Okay, so we want to take quotient of xn minus 1 with this thing. Okay, so let's go on and try to see. Okay, so consider the second map. The second map is given by this. Okay, so we are taking xn to taking quotient of xn with xn minus 1 minus en minus 1 beta. Okay, so in other words, we are collapsing this thing because we are taking quotient with this thing. So in other words, we are taking this thing to be a point. In other words, we are collapsing this thing to be a point. So for instance, okay, so in particular, let's try to see what's really happening here. In particular, if xn minus 1 is dn minus 1, okay, so then xn minus 1, which is in fact dn minus 1, we are taking quotient with this thing, and it is sn minus 1. Okay, so let's try to see why this is true. So for instance, let's take it to be d2. Okay, so take the inner cell. Okay, so of course we know that if we are writing down e2, then this is d2, and e2 is basically d2 without this boundary. Okay, so what we are doing is we are taking out the inner part, and of course this is going to be s1. Okay, so in other words, we are saying that take d2, take quotient of d2 with s1. Okay, so what is this s1? The boundary of d2. So what we are doing is we are taking d2 and we are collapsing the boundary of d2, which is s1, to one point. Okay, so in other words, take this circle and collapse this to a point, and if we will do that, we will basically get something like this. Okay, so when you will collapse this thing, then you will get s2. Okay, because when you collapse this circle to just one point, then you will get this s2. So that's what it means by collapsing xn minus 1. Okay, so collapsing xn minus 1 minus en minus 1 to a point. Okay, so now instead of this simple space dn minus 1, let's consider xn minus 1 to be any space. So what we are really doing is we are taking this en minus 1 cell out, and we are collapsing the rest of the space to just one point. Okay, so in this case the rest of the space was a circle, but then let's for example consider any space, take this n minus 1 cell out. Okay, so for example let's take this space, okay, this mouse. So take one disk from this mouse and then collapse the rest of the this mouse to just one point. Okay, so that will give me this map. Okay, so from the composition we have the map, this psi alpha beta, from Sn minus 1 to Sn minus 1, such that the degree of psi alpha beta is equal to d alpha beta. So remember that if we have a map from Sn minus 1 to Sn minus 1, then this will give me a map from Hn minus 1 Sn minus 1 to Hn minus 1 to Sn minus 1. Okay, so and remember that this is Z and this is also Z, and so the map is given by just multiplication by an integer, and that integer is the degree, and so the degree of psi alpha beta is equal to d alpha beta. So that's how we define this degree map. So in fact d alpha beta measures how many times the boundary of the n cell wraps around the n minus 1 cell. Since degree is computable, so the numbers can be computed. Okay, so once again try to consider this example, and you will see that this statement is true. Okay, so it measures how many times the boundary of the n cell wraps around the n minus 1 cell. Okay, let's try to consider another non-trivial example. We know that there are two kinds of manifolds. In particular, we are considering two manifolds. Okay, so orientable and non-orientable. Okay, so if it is orientable two manifold, then this is given as the connected sum of G torus. Okay, so where G is basically the genus of this two manifold. Now let's see how to calculate the cellular homology of this closed orientable surface of genus G. Okay, so basically it's a two manifold. So remember that if it is orientable surface of genus G, then this is going to be connected sum of G number of torus, and we have already discussed that. So for example, if we want to construct a torus, then we need one zero cell and two one cells, and then we can connect a two cell with it and we will get a torus. Okay, so that's how we get a torus. Similarly, we also discussed how to construct a two torus and the CW decomposition of two torus. So we need one zero cell, we need two one cells, we need four one cells, and then we can fill in these one cells to get a two torus. Okay, so something like this. Okay, so this is our point, this is our one cell, second one cell, third one cell, and the fourth one cell. Okay, so once again, if you are interested in the more detail, then I would recommend that you go back where we discuss this example. So in short, if we want to construct a genus G orientable surface, then we need one zero cell, we need two G1 cells, and we need one two cell. Okay, so we have the following associated cellular chain complex. So this is going to be our W2 mg, this is going to be our W1 mg, and this is going to be our W. Okay, so this is W0 mg. Okay, so I'm not going into the details of these degree maps, but if you're interested, I would recommend that you go to page 41 of Allen Hatcher. Okay, so where you can see that this D1 and D2 are 0, and if these are 0, then we will get the following homology of this mg. Okay, so let's begin with our second section of today's lecture, which is homology with coefficients. So the main question of this section is, can we compute homology in some group other than Z? So remember that I've told you, whenever we are constructing, whenever we are calculating the homology, whether it's simplicial homology or singular homology or cellular homology, then we are always taking the coefficients to be from the set of integers. So for example, if we are considering a cellular complex WNX, then it is basically a free abelian group generated by the n cells, okay, of the space X, and of course the coefficients are going to be from set of integers. Now the question is, can we compute homology in some group other than Z? The answer is yes. Okay, so it will run very similar to the constructions of simplicial and singular and cellular homology. So I'm going to skip these things very fast. So let G be a fixed abelian group. In this generalization, we consider chains of the form. So remember that when calculating the simplicial and singular and cellular homology, we took these ni's to be from the integers, and now we are taking these ni's to be from this abelian group G. Okay, so such chains forms an abelian group denoted by this. Now remember that instead of writing Cn of x, we are writing Cnx, this colon G, where G is the group where we are taking the coefficients from. Okay, so in other words, from now onwards, when we are writing down the integer homology, then I should write it down as this, so that it's clear that I'm taking the coefficients to be from the set of integers, okay, and not just from any abelian group. Okay, similarly we can define the boundary maps, and in the boundary maps it's once again very similar, and we can calculate that partial square is 0, and so this forms a chain complex. So once again notice that I'm writing down this extra G when I'm writing down these free abelian groups. Okay, and the resulting homology, in the resulting homology we also write down this G, and the rest of the things are same. So once again, if you want to differentiate this thing with the homology that we have discussed so far, that is with the coefficient Z, then we denote it as HNXZ. Okay, so similarly, if we want to calculate the reduced homology, then we introduce this extra bit where this epsilon is given as this. Okay, so the resulting homology is called the homology groups with coefficients in G. Okay, so on the same lines we can define relative homology groups where the coefficients are taken from this abelian group G, and once again you can notice that we are writing down this X and A because we are calculating the relative homology, and we are writing down this extra G here in order to make sure that we get that we are taking the coefficients from this abelian group G. And on the same lines we can calculate the cellular homology with coefficients from G, and remember that WKXG is going to be a free abelian group generated by K cells of X with coefficients from G, and this is also equal to this thing. And similarly we can calculate the degree maps. Okay, and this theorem can also be calculated. So all the theory developed for the homology in integers carries directly to the homology with coefficients with almost no change in the proofs. Okay, so for example we can use Meyer-Vittori's sequences, etc, etc, etc. So the differences between the integer homology and homology with coefficients from G begin to appear when we start calculating. Okay, so to compute efficiently we need the following theorem, which is the universal coefficient theorem. So in this theorem you can see some terminologies, you can see some things that we haven't discussed so far. So the idea is that we are not going to discuss them in very detailed way, and we are going to just see some of their properties which we are going to need in our calculation. Okay, so we have this short exact sequence, then our previous discussion from homological algebra, we can say that this is equal to the direct sum of this and this. So in other words, HKX Z, so in other words this is the homology with coefficients from integer tensor with G, and this we are taking the direct sum with this tor. Okay, so what is this tor and what is this tensor product? So once again we are not going to the detail, but we are going to need some properties of this tensor product and this tor. Okay, so what are those properties? So the properties are very simple. So Z tensor G is going to be equal to Z. Zm tensor Zn is going to be equal to Zd, where D is equal to GCD of M and N. So for example, if we want to construct the tensor product of Z2 and Z2, then we know that the GCD of 2 and 2 is equal to 2, so this is going to be equal to Z2. And similarly we can see the properties of tor. So tor of AB is equal to tor of BA, and tor of 0B is equal to 0, tor of Zn, Z is equal to 0, tor of Zn, Zm is equal to Zd. So once again you can see that tor of Z2 and Z2, so this is going to be equal to Z2. Okay, so because D is the GCD of M and N, and if G is equal to Q, R or C, then tor of AQ is equal to 0. So in this case the computation of the homology becomes easy, because if G is equal to Q, R and C, then the tor is equal to 0. So let's go back to this formula. So if this is 0, then the homology, okay, so the homology with coefficients from G is equal to just taking the tensor. So in other words, if we are considering the homology with coefficients from rationals or reals or complex, then we just need to do the following thing. So in other words, we can say that HK of X Q, okay, so this is equal to HK x z tensor with q. Okay, so roughly speaking, you can say that in this tensor product, I'm replacing the integer coefficients with the rational coefficients. Okay, so in other words, if we want to calculate hk of xq or hk of xr or hk of xc, then what do I need to do? Just take the tensor product of the integer homology with this group. So for example, if we are taking c, so hk xc, this is going to be equal to this. So once again, we are replacing the integer coefficients with the complex numbers. Okay, so just write down the coefficients. Okay, so we know that we calculate the homology by taking the quotients of the kernel, quotient the image, and in that kernel and image we take the coefficients to be from the set of integers, but this thing is saying that take the coefficients from set of complex numbers. So that's how simple it is if we take G to be equal to Q, R or C, because in this case TOR is 0. And similarly, we have some other properties. So it says that if we have a direct sum on the first part, then this direct sum can come out, and similarly if we have direct sum on the second part, then this direct sum can also come out. So let's apply this universal coefficient theorem to calculate the homology of this n-dimensional projective space with coefficients from Z2. So we know the integer homology of the projective space, and it is Z if I is equal to 0 or n, and n is odd. Okay, and this is Z2 if I is odd and I lies between 0 and n, and this is 0 otherwise. So basically we have three cases. Let's calculate these three cases and using this universal coefficient theorem. So what do we need to calculate here? So we need to calculate the homology with coefficients from Z2, so homology of n-dimensional real projective space. So let's consider the case number 1, where I is equal to 0 and I is equal to n, and n is odd. Okay, so in this case this homology is Z, so basically we can say that hk of x z is equal to z, and remember that in this case or G is equal to Z2. So let's go back and try to see the properties of tensor product. So Z tensor with G is equal to G. So in other words, so this becomes Z tensor Z2. Okay, so let's go to the next step. So in this case G is equal to Z2, and what about this thing? Okay, so if I is equal to 0, then of course this is 0. Okay, because then if I is equal to 0, so in this case of course this I is not I, this is k. If k is equal to 0, then h minus 1 is 0 definitely, and if n is odd, then n minus 1 is even, and this third case says that this is going to be equal to 0. So if I is equal to 0 or I is equal to n, this thing is going to be 0, and we know from the property of TOR that if this first coefficient is 0 or the second coefficient is 0, because due to the first property they are symmetric in this way. So if one of these we can roughly say that coordinate is 0, then basically this is 0, so this becomes 0 in this case, and so we are taking the direct sum with 0. So Z tensor Z2, let's go back again, Z tensor Z2 is Z2, so this is going to be equal to Z2. Okay, so what do we need to show? We need to show that this is always Z2 when I lies between 0 and n, and we proved this thing in the case when we have I is equal to 0 or I is equal to n and n is odd. Let's go to the second case. Let's see how to show the second case. Okay, so in the second case I is odd and I lies between 0 and n. So this is our case 2. Okay, so once again we want to use this theorem. So this theorem says that this universal coefficient theorem x g, so the homology with coefficients from g is equal to the homology with coefficients from z, take its tensor with g and take its direct sum with tor h k minus 1 of x z and g. Okay, so let's see. So in this case we have this homology to be z2, okay, and z2 tensor z2. So from our previous computation, z2 tensor z2 is just z2. Okay, so in this case this is z2, and if I is odd, then once again k minus 1. So if once again we are taking I to be equal to k, so if k is odd, then k minus 1 is even, and we know that from the homology of the real projective space, if I is even, then this is 0, so this is 0 again, and so this is equal to z2 tensor z2, and we know that z2 tensor z2 is equal to z2. So in the second case we also proved that the homology with coefficients from z2 is going to be z2 for real projective space. Let's come to case number 3. In case number 3 we want to discuss the case where I could be anything, but so basically it's not odd, okay, and it's not 0, it's not n. So let's write down the theorem, the universal coefficient theorem. So in this case this homology with coefficients from g is going to be equal to the homology with coefficients from z tensor, okay, with g plus tor h k minus 1 x z g. Okay, so in this case let's see what is going to be this homology. So this is going to be 0. Okay, so 0 tensor z2 is going to be 0. Okay, so let's discuss this thing. So tor. So once again, if k is even, then k minus 1 is odd. If k minus 1 is odd, then we know that this is going to be z2, and the group is also z2, and we know that tor of z2 is equal to z2 because 2 is the GCD of 2 and 2. So using the property of tor, we also proved in the third and last case that the homology with coefficients from z2 of a real projective n space is z2. Let's begin with our next section of today's lecture, which is covering spaces. So given a topological space X, we know how to calculate the fundamental group. In this section we will see that any topological space X can be obtained as quotient of a simply connected space using the notion of covering space. So in other words, you can say that this section is going to be very connected to our discussion of fundamental group. Okay, so given any space, we want to construct a simply connected space such that when we take quotient, okay, so what is quotient? We will discuss this in our further discussions. So when we take the quotient of that space, then we will get that topological space. So what is this discussion of covering space about? So in covering space we usually have two spaces. For example, the space X and the space Y. Okay, so this space, okay, so in this case this is B in fact. So this is the base space. So X is called the covering space and B is called the base space, and this P is covering map or sometimes projection. Okay, so in this section we will be discussing how to construct X and given any base space. So starting from a very important example of this section of covering spaces, so consider this map P from R1 to S1. Okay, so what is this map? So in fact we are projecting a helix on a circle such that each point of R1 is mapped to a unique point of the circle. So in other words, take this real line and turn it around like this. Okay, so turn it around like this and it will become a helix. Okay, so we are not changing the topology of this real line while we are doing that. So in other words, this helix is the same as this R1. And now what we are doing is we are basically taking the points of the helix to the points of the circle. So for example, take this point and we are taking the image of this point to be this point on the circle. And similarly, take this point and we are taking the image of this point to be this point on the circle. And similarly, take this point and we are taking the points in this and this up to so on. So take any part of the helix and we can project that point onto the circle. Okay, so on the other hand, given any point x belongs to S1, the inverse image P inverse x is union of points of R1. So let's say this is a point on the circle, then its inverse image, because this P is basically mapped from R1 to S1, and we already discussed that what is this map, but the inverse, so the inverse of this one point is going to be infinitely many points. So for example, the inverse of this is basically this point, so x1, this point x2, this point let's say x minus 1, okay, up to so on. So P inverse x is going to be equal to x naught, x1, x minus 1, x2, x minus 2, up to so on. So this is going to be P inverse x. Okay, so this is basically a very typical case of covering spaces where we are covering this circle with this real line. Okay, so we can project the points of R1 to the circle and we can take the inverse image of the points of circle and we will get infinitely many in this case. Okay, so there could be finitely many as well. We shall see some other examples. So let's try to define what are covering spaces. So a covering space of a space X is a space X tilde together with the continuous function satisfying the following condition. So X tilde should be path connected topological space. So we can easily see that in our previous example, this R1 is path connected topological space, and this map P is basically a continuous map. So we shall see this, we shall see the continuity of this map when we will define it precisely in our further discussion. Okay, so for each x belongs to capital X, there exists an open neighborhood U such that P inverse U is union of open sets UI such that P restricted to UI to U is a homeomorphism. So in other words, what we are saying is, consider once again this example of a circle and take this point X and take an open set around X. So let's call it U. Take the inverse image of this U. So the inverse image is going to be this set, okay, and this set, and up to so on. So it's going to be infinitely many. So let's call it U0. So let's call it U1, U2, U minus 1. Okay, so the condition is that when we restrict this P to this UI, then this map from UI to U is a homeomorphism. Okay, so this is our map P where we are taking the points of the real line to the circle, and now it says that, okay, so it says that P inverse U is disjoint union of open sets. Okay, so P inverse U is disjoint union of open sets, U1, U2, U minus 1, up to so on. And also, if we restrict this P to just this U1, okay, so P restricted to U1, it's going to be a map from U1 to this U0, it is homeomorphism. Okay, so roughly speaking, the neighborhood, okay, so the P inverse U is going to give me neighborhoods of the point x1. So locally in this copy, in this portion of the covering space R1, which in this case, so this part is homeomorphic to this part, and this is union of many disjoint open sets. Okay, so all of these sets are homeomorphic to this open neighborhood of X. So in other words, we can say that if we are on the covering space, then locally this covering space looks like the same as the space X. Okay, so locally around this X1, this space looks like the same as the space as the neighborhood of X. Okay, so these are homeomorphic. In other words, topologically there is no difference. Okay, so we denote the covering space as X tilde and P because we need these two things. We need this topological space X tilde, which is of course path connected according to our definition, and this P, which is a continuous map. So the map P is called covering projection. Let's come back to our example again. So we can define this P in the following way: P of t, where t is any real number, is equal to e raised to power 2 pi I t, and it can be seen that P is a covering map, it's a continuous map, R1 is a path connected space, and if we take any point on the circle, then P inverse is going to be disjoint union of open sets, and each and every open set is homeomorphic to this U. In other words, the covering space locally is homeomorphic to our base space. Okay, so that's one of the fundamental properties of the covering space, that locally it's the same. So locally it's homeomorphic to our base space. Okay, so we know that real projective